On November the 6th, 1919, a room full of the most skeptical men in Britain sat in the halls of the Royal Society and listened to the Astronomer Royal read out a single number, 1.75 arcseconds, the exact bend in starlight that Einstein's 4-year-old theory had predicted, and Newton's much older one had gotten exactly half right. 59 years after that, astronomers confirmed that a distant pair of dead stars was spiraling slowly into itself by losing energy to gravitational waves nobody on Earth had yet built an instrument sensitive enough to detect directly. Indirect evidence, but ironclad, that Einstein's ripples in spacetime were physically real. 37 years after that, in September of 2015, two 4-kilometer steel tunnels, one in Louisiana, one in Washington State, twitched by an amount smaller than the width of a single proton, and human beings heard, for the first time in the history of our species, the actual sound of two black holes colliding 1.3 billion years ago. We predicted it. Then we confirmed it indirectly. Then we recorded the waveform directly. And after all three of those things happened, go ask an intelligent, well-read adult what gravity actually is, and 9 times out of 10 they'll tell you, with real confidence, that nobody's ever fully explained it. They'll say Newton had a force, and it worked fine, until it didn't. They'll say Einstein came along and said, essentially, it's not a force, it's curved space. And they'll say this like they're handing you the answer, when what they've actually handed you is a rephrased version of the question. Space is curved. Fine. Curved how? Curved into what? Why does bending a direction make an apple fall out of a tree? Push most people one sentence past their own explanation, and they stall. They've got the vocabulary. They don't have the mechanism. And the reason that matters, the reason I'm spending the next while on it, is that this isn't a harmless gap in public trivia. It's a specific, structural misunderstanding, and it's aimed at the wrong half of the story. Gravity is not the mystery. It hasn't been the mystery since 1915. What's still genuinely unresolved this morning mysterious is space-time itself. And until you separate those two questions, you'll keep mistaking a solved problem for an unsolved one, while walking straight past the actual unsolved one without noticing it was ever there. Here's a place to start that most documentaries skip, because it makes Newton look bad, and popular science has a strange soft spot for protecting Newton. In 1693, he wrote a private letter to a theologian named Richard Bentley, and said something that never makes it into the 9th grade textbook with his name on the cover. He said the idea of gravity being innate to matter, one body reaching across empty space and pulling another with nothing at all in between, no medium, no contact, no mechanism, was, in his own words, so great an absurdity that he didn't think any competent thinker could accept it. Newton, telling a friend, in private, that his own most famous law didn't actually explain anything. It described, with staggering precision, what happens. It stayed completely silent on why. He had a phrase for this later. Hypotheses non fingo. I frame no hypotheses. Translation? I can tell you exactly how fast the apple falls, and exactly how the moon curves around the Earth, to the decimal. And I'm not going to pretend I know why any of it is actually occurring. That admission sat there, unresolved, for 222 years. 2 centuries of astronomers using a tool that predicted planetary motion with almost supernatural accuracy, built by a man who told his friends in private letters that he found the whole premise faintly embarrassing. Then, in 1915, a physicist working mostly alone did something nobody was expecting. He didn't go looking for the mechanism behind the pull. He got rid of the pull. I learned the difference between a description and a mechanism in a small examination room, years before I'd ever thought seriously about physics. I was a biochemist by training, deep in enzyme kinetics, defending a dissertation on how biological catalysts speed up reactions, and one of my examiners asked me to explain, in mechanistic terms, why a particular enzyme lowered the energy a reaction needed to proceed. I gave him an answer full of the right vocabulary: active site, transition state, binding affinity. He let me finish, and then he asked one more question. You've told me what we call it. Now tell me what it does. I didn't have a good answer that day. It took years of actual bench work before I understood what he'd been pointing at. That naming a phenomenon precisely, even in the correct technical language, is not the same as describing the physical steps by which it happens. A label can hide inside an explanation for a long time before anyone notices it isn't one. I think about that exam every time I hear someone say, space is curved, and stop right there, satisfied, because curved space is exactly that kind of label. It's correct. It is not yet a mechanism. So let me hand you the mechanism, right now, so you can feel the difference for yourself. I need you to slow down with me here, because this next part is the actual hinge the rest of the subject turns on. Picture yourself in an elevator with no windows, and the cable snaps. For the few seconds before it hits bottom, you'd feel weightless. Completely weightless. The identical sensation astronauts feel aboard the International Space Station. Not almost the same. The same physics. Here's the part that should stop you. Astronauts orbiting Earth are also in free fall. The station sits about 250 miles up, well inside Earth's gravitational field, experiencing roughly 90% of the pull you're feeling in your chair right now. It is falling. Constantly. It just happens to be moving sideways fast enough that the curve of its fall matches the curve of the planet underneath it, so it falls forever without ever hitting anything. An orbit is not the absence of gravity. An orbit is a very long, very graceful fall that keeps missing the ground. Einstein called the insight behind this, that free fall and weightlessness are the same physical state, not a similar one. The happiest thought of his life. And once you see why, the description stops sounding sentimental. If a person in free fall feels zero gravity, not reduced gravity, zero, then gravity isn't something being applied to that person. It's something that stops being applied the instant they stop resisting it. Which means the weight in your legs right now, this second, isn't a force reaching up out of the earth and grabbing you. It's the floor, refusing to let you fall. You are being continuously, physically prevented from plunging toward the planet's core, and what you call gravity is the effort of the ground shoving back against that fall. You are, right now, accelerating upward at about 9.8 meters per second every second. The same figure that describes a rocket leaving a launch pad. And you are not moving 1 inch. That is not a metaphor. It is the literal claim general relativity makes about your own body as you sit here. So if gravity isn't a pull, what is it? Rebuild it with me, one piece at a time, no skipped steps. Mass and energy sit inside a 4-dimensional structure, 3 dimensions of space and 1 of time, stitched into a single geometric object physicists call spacetime. Not for poetry's sake, but because once you're moving near the speed of light, distance and duration trade off against each other, and treating them as one combined structure is the only way the mathematics stays consistent. Mass doesn't sit on top of that structure like a bowling ball on a trampoline, the image you've seen in every single documentary on this topic. Because that picture uses gravity to explain gravity. It shows a ball sinking into a sheet because of gravity, to illustrate gravity. What actually happens is stranger and considerably cleaner. Mass and energy change what straight means in the region around them, and everything in that region. An apple, a planet, a beam of light, keeps moving in the straightest line available to it. The apple isn't pulled downward. The straightest available line, in the warped geometry around a planet-sized mass, simply ends at the ground. Nothing pulls the moon toward the Earth. The moon travels a straight line through a region of space-time that Earth's mass has bent into a curve, and a straight line through curved geometry looks, from outside, exactly like an orbit. There's a piece of infrastructure sitting somewhere above your head right now, one you probably used this morning without a second thought. running a live experiment in exactly this idea, every second, and getting it right to a precision most sciences would call a miracle. Every GPS satellite carries an atomic clock, and those clocks disagree with clocks on the ground in two separate, opposite ways. Because the satellites move at roughly 14,000 kilometers an hour, special relativity says their clocks should run slow by about 7 microseconds a day, purely from speed. But because they orbit 20,000 kilometers up, in a much weaker gravitational field than the surface of the Earth, general relativity says their clocks should run fast by about 45 microseconds a day, purely from being farther from the mass beneath them. Deeper spacetime curvature genuinely ticks time slower, shallower curvature ticks it faster, and this is the actual mechanism, not an illustration of one. Net the two effects and satellite clocks gain about 38 microseconds every single day compared to a clock sitting next to you right now. 38 millionths of a second doesn't sound like something worth engineering around. Except the entire GPS system depends on comparing signal timing down to nanoseconds, and if that 38 microsecond drift went uncorrected, your phone's position would be wrong by about 10 kilometers by the end of the first day, and it would keep getting worse. So the engineers who built GPS didn't treat spacetime curvature as an interesting philosophical footnote. They physically detuned every atomic clock before launch, shaving its oscillation frequency down in advance so that once curvature sped it back up in orbit, it would land exactly on the correct rate. That correction is baked into hardware that's currently sitting in a satellite 2 Earth diameters above your head. This is the same wrong idea I opened with, wearing a lab coat. The assumption that curved spacetime is just poetic packaging around Newton's same unexplained pull. It isn't packaging. It's not a metaphor being politely tolerated by physicists because it sounds nice in a documentary. It's an engineering constant, computed to the microsecond and compensated for by the phone in your pocket, dozens of times a second, to keep your blue dot in the right place on the map. A metaphor has never once told an engineer exactly how many nanoseconds to shave off an oscillator before bolting it to a rocket. A mechanism does that. This one does that, right now, over your head. There's a second confirmation of this same mechanism that arrived even before satellites existed, decades before GPS. And it's arguably the most emotionally satisfying piece of evidence in the entire history of the subject, because of exactly how specific the number is. Mercury's orbit doesn't stay perfectly still in space. Like every planet, its elliptical path slowly rotates, and by the late 1800s, astronomers had accounted for essentially all of that rotation using Newtonian gravity, factoring in the tug of every other planet in the solar system. Almost all of it. After every known correction, there was a stubborn leftover. 43 arcseconds per century that Newton's law simply could not produce, no matter how astronomers adjusted the input masses. For decades, the leading guess was that an undiscovered planet, provisionally named Vulcan, was hiding close to the Sun, tugging on Mercury from an angle nobody could see. Astronomers searched for Vulcan for over half a century. It was never there. In November of 1915, Einstein applied his still unfinished field equations to Mercury's orbit as a test case, with no fudge factors, no planet invented to make the numbers work, and got out 43 arcseconds per century. Exactly the leftover. Exactly the anomaly that had embarrassed astronomers for 2 generations. 4 years after that, the 1919 eclipse expedition measured how much starlight bends as it grazes the Sun. And here the two competing theories made genuinely different predictions you could actually go check. Newtonian physics, treating light as tiny particles with mass, predicted a bend of 0.87 arcseconds. Einstein's finished theory predicted exactly double that, 1.75 arcseconds, because in general relativity the deflection comes from warped space itself, not merely from light being weakly tugged like a thrown ball. Arthur Eddington's team measured 1.98 arcseconds from Brazil and 1.61 from an island off West Africa. Close to Einstein's number, nowhere near Newton's. That's the number Dyson stood up and read to the Royal Society on that November afternoon in 1919. Overnight, the man who 6 years earlier had privately called his own theory a metaphor propped up by curved space language, in the sense that it hadn't yet been tested against reality, became the most famous scientist alive, because his metaphor had just made a prediction accurate to a fraction of an arcsecond about an anomaly that had haunted astronomy for half a century. I want to stay on this a moment longer, because there's a habit smart people fall into here that's worth naming directly. Treating curved spacetime as a rebranding of Newtonian force, a coat of paint on the same unexplained pull. It is not the same claim wearing a costume. It is a structurally different claim that happens to agree with Newton's numbers in weak fields and disagrees with him, measurably, in strong ones. And every single time the two theories have made different testable predictions, from Mercury's orbit to the bending of starlight to the ticking rate of a clock 20,000 kilometers overhead, reality has sided with Einstein's version, not Newton's. That's not what a synonym does. That's what a genuinely different and more correct description of the physical world does. Years after my dissertation defense, once I'd moved from the bench into a lecture hall, I found myself using almost the same move on undergraduates that my examiner had used on me, usually around the third week of the semester, when a bright student would explain enzyme catalysis by saying, "The enzyme makes the reaction easier." I'd stop them and ask what easier cashes out to, physically, at the level of atoms and bonds. And the honest answer is that a catalyst lowers the energy barrier a reaction has to climb by holding the reacting molecules in precisely the geometry that makes the transition state cheaper to reach. Nothing mystical happens. The molecules aren't persuaded. They're geometrically arranged so that the straightest, lowest cost path through chemical possibility space happens to be the one that leads to product. I did not expect, spending years teaching that particular idea to sophomores, that it would turn out to be close kin to the deepest idea in general relativity, that changing the geometry of a system changes which path is cheapest, and everything in the system will, without exception, take the cheapest path available to it. An enzyme reshapes chemical possibility space so the easiest route leads somewhere useful. A planet reshapes spacetime so the easiest route for a moon, an apple, or a beam of light leads into a curve. Different fields, same underlying grammar. Shape the terrain, and you no longer need a force to explain where things end up. You only need to know what straight means in that terrain, and everything else follows without anyone having to push anything. There's a picture I want to put in front of you now, because up to this point, everything I've described has been indirect. Numbers on a page, drift in a satellite clock, arcseconds nobody but astronomers ever look at directly. On April the 10th, 2019, that changed. A worldwide collaboration called the Event Horizon Telescope released the first actual image of the edge of a black hole. Not an illustration, not an artist's rendering, an image built by linking radio dishes on mountaintops from Hawaii to the South Pole into a single instrument, effectively the size of the Earth, all synchronized to atomic clocks, precise enough that an error of a few nanoseconds in the data would have ruined years of work. The target was the supermassive black hole at the center of a galaxy called Meters 87, 55 million light-years away, with a mass of roughly 6.5 billion suns. What came back was a lopsided orange ring around a dark center. Light from superheated gas, bent by the black hole's gravity into a circle about 2.5 times wider than the event horizon actually sitting inside it, exactly the shape general relativity had predicted for that specific mass at that specific distance, decades before anyone had the technology to go check. 3 years later, the same collaboration released a second image, Sagittarius A, the black hole at the center of our own galaxy. Here's the number I want you to sit with, because it's the kind that should make you feel faintly dizzy. Sagittarius A is about 4 million times the mass of the Sun. M87's black hole is about 6.5 billion times the mass of the Sun, roughly 1,500 times heavier. And yet, in both images, the ring looks almost exactly the same size in our sky. Not because the physics disagrees with itself, but because Sagittarius Aber sits 27,000 light-years away, while Meters 87 sits 55 million light-years away. Close enough, relative to its own staggering size, to appear almost the same angular width as a black hole 1,500 times smaller and roughly 2,000 times closer. Two wildly different masses, two wildly different distances, and general relativity told astronomers, in advance, exactly what ring diameter to expect from each one. That's not a theory being interpreted charitably after the fact. That's a theory being handed a blank photograph in advance and correctly filling in what would appear on it. I was watching the first announcement live, the Meters 87 one, sitting in a common room with colleagues considerably younger than me, most of whom had grown up with this theory as settled background fact, the way I'd grown up with the periodic table already arranged into rows. And I remember the specific, slightly disorienting sensation of an argument I'd been making in lecture halls for the better part of my career quietly stop being an argument and become a photograph instead. You can dispute an argument. People had, for decades, in exactly the sloppy language I opened this with. A force renamed, a mystery repackaged with better lighting. Nobody in that room was disputing a photograph. If you still want to tell me that curved space-time is just a fancier phrase for the same old unexplained pull, I'd ask you to explain, using Newtonian gravity alone, why two black holes 1,500 times different in mass-produced rings of almost identical apparent size on two separate continents' worth of radio dishes. Newton's law has no mechanism that predicts that number. General relativity does, because it was never describing a force to begin with. It was describing a shape. And shapes, unlike forces, can be photographed. There's a decade of my life I haven't mentioned yet. One I actually think matters more to this topic than the classroom does, because it's where I got caught being wrong in public and had to fix it in public, which is a different kind of education entirely. Wrote science fiction on the side for most of my working life, mostly for pulp magazines that paid badly and edited aggressively, and I had a running argument for years with one particular editor about faster-than-light travel, whether a story could use it and still call itself hard science fiction. I took the position, loudly, more than once, that as long as you didn't specify a mechanism, you weren't technically breaking any law of physics. You were just being vague, and vagueness wasn't the same as violation. My editor, who read far more physics than most editors bothered to, tore that argument apart in the margins of a returned manuscript with a single sentence. Vagueness about how you're breaking a rule doesn't mean you're not breaking it. He was right, and I hated that he was right, and the argument sent me back to general relativity with much more care than I'd given it before, because I needed to actually understand what faster-than-light travel would cost a story if I wanted to use it honestly. What I found is worth pausing on. Nothing in relativity forbids space itself from moving faster than light. The speed limit applies to things moving through spacetime. It says nothing about spacetime itself stretching, compressing, or rearranging its own geometry, which is exactly what's happening right now at the edge of the observable universe, where galaxies are receding from us faster than light purely because the space between us and them is expanding. Space is not a thing sitting still while things move through it at a maximum speed. Space itself has no speed limit imposed on it, because the speed limit was never a rule about geometry. It was a rule about motion within geometry. I lost that argument with my editor, and I'm still grateful for it, because losing it is the only reason I understood the difference. Now here's where I have to be honest with you about something that still genuinely unsettles me, more than 2 decades into thinking about this subject professionally. And I don't say that as a rhetorical device to make myself seem humble. There is a specific place where this beautiful, smooth, continuous geometric picture I've just spent the last several minutes rebuilding for you simply stops working. And nobody, not me, not anyone currently alive, has a fully agreed upon fix. Black holes have event horizons, boundaries past which nothing, not even light, can climb back out. In the mid-1970s, Stephen Hawking showed that black holes aren't perfectly black after all. They leak a faint trickle of radiation, now called Hawking radiation, and given enough time, they slowly evaporate away entirely. That result, on its own, is a triumph, another confirmation that quantum effects and gravity can be talked about in the same sentence. But it also opens a trap door. If a black hole eventually evaporates completely, what happens to the information about everything that ever fell into it? Every atom's exact quantum state? Everything that in principle should be perfectly preserved because quantum mechanics forbids information from simply vanishing from the universe? Hawking's own calculations suggested the radiation coming back out is essentially random, carrying no trace of what went in, which would mean information really is destroyed, which would mean one of the two foundational pillars of modern physics, the unitarity of quantum mechanics, is just wrong, in exactly the regime where general relativity and quantum theory are forced to speak to each other. Physicists have spent 50 years trying to close that gap, and there are candidate answers. The idea that information leaks back out, encoded subtly in the radiation itself, the idea that space-time near the horizon isn't smooth at all, but ends in something researchers have called, only half-jokingly, a firewall. But none of it is settled the way Mercury's orbit is settled, or the way GPS timing is settled. I have spent my working life defending the idea that space-time is the real, physical, geometric stage on which the universe happens, and I have to tell you honestly that at the one place where we've actually tried to look closely at the seam between that stage and quantum mechanics, the stage doesn't obviously hold together. That bothers me. It should bother you too. And if a documentary tells you this is all cleanly resolved, it is being kinder to you than the actual physics currently allows. Here's the piece of experimental confirmation I want to leave you with before we get to where all of this actually points. Because it's the moment space-time itself stopped being describable only through its effects on other things and became something we could listen to directly. On August 17, 2017, LIGO and its European partner Virgo detected gravitational waves from two neutron stars spiraling into each other and merging, and this time, unlike the black hole mergers detected before it, the collision also produced light. A burst of gamma rays picked up by an orbiting telescope. That gamma ray burst arrived 1.7 seconds after the gravitational waves did. The signal had traveled about 130 million light-years to reach us. Do the arithmetic on that. A crossing of roughly 4,000 trillion seconds with the two signals, one made of gravity, one made of light, arriving within less than 2 seconds of each other. That measurement pinned the speed of gravitational waves to the speed of light to within 1 part in a quadrillion, not roughly the same speed. The same speed to a precision most physical constants never achieve at all. Gravitational waves aren't a mathematical convenience invented to make equations balance. They are physical ripples in the actual geometry of space-time. They carry energy. They travel at a fixed, finite, measurable speed. And 4 years earlier, in that first detection in September of 2015, they physically stretched and squeezed 2 4-kilometer steel tunnels by roughly 1,000th of the width of a single proton, a distortion so small that engineers had to build the most precisely calibrated measuring device in the history of the species just to catch it, and they caught it anyway. You cannot do that to a metaphor. You can only do that to something physically real. So take stock of where that leaves the argument. Gravity's action. What it does, how strongly, in what direction, at what rate, has been correctly and completely described since 1915, confirmed by Mercury's orbit, by starlight bending exactly twice as much as Newton predicted, by clocks on satellites ticking at engineered rates to compensate for real curvature, by tunnels in Louisiana flexing by less than a proton's width when space-time itself rippled past them. There is no remaining mystery in what gravity does. If that's the case you were bracing to have with me, you've already lost it. because the evidence closed that case a century ago, and reality has never once sided with the alternative. But space-time, the actual thing doing, the curving, the medium in which all of this plays out, is a different question entirely, and it's wide open. Is space-time fundamental, a genuine, irreducible ingredient of reality, or is it made of something more basic, the way water is made of hydrogen and oxygen, even though water feels perfectly continuous when you swim through it? A growing body of serious theoretical work, building on the holographic principle from the 1990s, and later work explicitly connecting space-time geometry to quantum entanglement, suggests that space itself, the very thing gravity curves, might be constructed out of a network of entangled quantum information, the way a smooth photograph is constructed out of pixels too small to individually notice. If that turns out to be right, and it is genuinely not settled, then the black hole information problem I just admitted I can't close stops looking like a stray loose thread and starts looking like a symptom, a place where the stage of space-time, examined closely enough, shows you it was never the fundamental floor of reality to begin with. It was already the second layer down. Think about what that actually means, if it holds up. Not that gravity is mysterious. We've settled that, and settled it more thoroughly than almost anything else in physics. It means that space and time, the two things you have never once in your life questioned, the two things every single sensation you've ever had has been arranged inside of, might not be bedrock. They might be the emergent, large-scale behavior of something underneath them that doesn't look like space or time at all. The way temperature is a real, measurable, physically meaningful property of a gas that completely disappears if you zoom in far enough to look at a single molecule, because a single molecule doesn't have a temperature. Maybe space-time is like that. Maybe here and now are the readable, average, zoomed-out behavior of something with no here and no now built into it whatsoever, and what gravity is actually doing when it curves a path around a star is showing you the visible seam of that underlying structure. The one place, the zoomed-out picture, leaves fingerprints of the zoomed-in one. I'll tell you plainly where I personally land on this, because false modesty has never once helped a student, and it isn't going to start helping you now. I think space-time is probably not the fundamental level of reality. I think it's closer to the surface than a century of textbooks, mine included, have been comfortable admitting. And I think whoever is watching this a few years from now, not whoever wrote it, is the one who gets to find out for certain. That is not a small thing to hand off to the next room full of graduate students. I have spent most of a working life defending the idea that space and time are the real, physical, load-bearing stage the universe stands on. I am telling you, plainly, that I now think the stage is probably scaffolding for something underneath it that doesn't have a name yet, and quite possibly doesn't have a place or a moment built into it at all. You didn't come here needing someone to explain gravity to you. Gravity stopped being the hard question in 1915, and it has stayed answered for 111 years. That argument is over. And it was over before your grandparents were born. What nobody handed you, what almost nobody ever gets handed, is the honest version of the question sitting underneath it. The floor you have never once doubted. The one thing every sensation of your entire life has happened on top of might not be a floor at all. It might be a shadow. The same kind of shadow that made headlines in 2019. A dark silhouette cast by something whose true edge you can't quite see directly, only infer from the light bending around it. Gravity, the thing you walked in here worried about, was never the mystery. It was only ever the one place the shadow got thick enough for you to finally notice it was there.